In this segment, we're going to talk about common steady flow devices, specifically nozzles and diffusers. Now, many engineering devices are operating under the same conditions for a long period of time. For example, what you see here looks like we're on the floor of a turbine building, and you've got a couple of turbines beside each other. And we're going to talk about those in more detail later. But what it looks like is that if I looked at the operating conditions at 11 o'clock and then I went and got some lunch and I came back at 12, the operating conditions are probably not going to have changed. So like the inlet and the outlet conditions of these devices are not going to have changed because everything's it's operating as it normally does. And so devices in such a situation would be analyzed at essentially steady state. Now, there are lots of times where that assumption is not appropriate. For example, if you're bringing the system online, or if you're bringing the system down to do maintenance on it, for example. And there are lots of other cases where that assumption wouldn't be appropriate, but most of the time in this class, we're going to be analyzing systems that are operating at steady state. All right, now nozzles and diffusers. So here's a nozzle, and what you can see is the cross-sectional area is decreasing from the inlet to the outlet. And you see that a nozzle, as you might guess, speeds up flow. So you're familiar with a garden hose nozzle. It speeds up the flow. A diffuser does just the opposite. So the cross-sectional area increases from the inlet to the outlet and the velocity slows down. It has a different effect on the pressure. So for a nozzle, the pressure decreases from the inlet to the outlet. So the pressure at the outlet is lower. Opposite for a diffuser, it increases as it passes through. And sometimes this pressure part, this is sort of a sticking point for students. So we're going to kind of come back around and show why that relationship exists at the very end. But let's look at how we analyze these devices. First thing I'm going to do when I'm interested in analyzing an open system is I need to apply my conservation of mass. I need to know how the m dots are related to one another. So here's my conservation of mass, and now I'm going to apply some appropriate assumptions. First thing I'm going to do is I'm going to assume that it's operating at steady state, and that'll simplify my math quite a bit. So I've got the sum of the m dots at the inlet minus the sum of the m dots at the outlet, and I've only got one inlet and one outlet. So I've got 0 equals m dot 1 minus m dot 2. Looks like those are equal to one another, so I could just drop that subscript and just refer to the mass flow rate going through as just m dot. All right, so now I'm ready to apply my conservation of energy, and I need to make sure that I pick the appropriate version of the first law because I've got one for a closed system, one for an open system, and I have definitely got an open system because I've got mass flowing in and mass flowing out. So here's my conservation of energy, my first law, and because it's operating at steady state, I go ahead and get rid of that DETT. Now for nozzles and diffusers, what we're going to do now is we're going to list some commonly applied assumptions. And these assumptions are going to be assumptions that you need to memorize. So number one, we're going to ignore the heat transfer. Typically your fluid is not spending a lot of time within that nozzle or within that diffuser. And so the heat transfer, it's not going to give a lot of time for heat transfer to occur. It doesn't mean that there's not any heat transfer. I mean, obviously, if you've got a really, really hot fluid going through a nozzle or a diffuser and the environment is a lot colder, well, yeah, you're going to have some heat transfer. Maybe you'd have to consider it then. But typically, you can go ahead and ignore it. So in this class, you can go ahead and ignore it unless you are explicitly told otherwise. So like if you are explicitly told that you've got a heat transfer rate of such and such, then go ahead and factor that in. Otherwise, just ignore it. Don't have any power or don't have any work. So you've got flow work, but that's accounted for with the enthalpy term. And there's no shaft work or electrical work or anything like that going on. So that W dot is just 0. And then you don't really have any potential energy change. You don't have any great elevation change with this. And so that's going to go away too. So here's what I'm left with. I've got the m dots, the enthalpy, and the kinetic energy term. And now, well, let me just kind of get rid of those summations. So I've got one inlet and one outlet, so I'm still left with just two terms. And then I'm going to look back at my conservation of mass, and I'm going to realize that m dot 1 and m dot 2 are equal to one another. So I'm going to go ahead and factor that into things, and then I'm just going to divide through by m dot and get rid of them. So here's my simplified version of the first law for a nozzle or a diffuser. Now, one extra assumption that you can make for a nozzle or for a nozzle, you see that it speeds the flow up. So the velocity at the outlet is bigger than the velocity at the inlet. Now, if I look at that first law, I see that those velocities are squared. So if V2 is bigger than V1, V2 squared is going to be a lot bigger than V1 squared. And so if you don't know the velocity at the inlet, you can go ahead and ignore it and just say that it's approximately 0. And then with a diffuser, same kind of argument. If you don't know the velocity at the outlet, it slows things down, and so that V1 squared is going to be a lot bigger than the V2 squared, and so you can just go ahead and ignore that V2 squared term. All right, so what causes, or why does the pressure decrease through a nozzle? So like I said, sometimes this is a sticking point. So what we're going to do is we're going to look at a nozzle, and we're going to start with that first law. So I've got, this is not ignoring the kinetic and potential, or the kinetic energy changes yet, but I'm going to go ahead and say for a nozzle, let me get rid of that V1 squared just to make things a little bit more simple. All right, and now what I'm going to do is I'm going to put that enthalpy term in terms of internal energy and pressure and specific volume, so U plus PV. And now for flow through a nozzle, your internal energy is not going to change as much as PV, which you could refer to as pressure energy. And that makes sense, right? Internal energy is very much tied to the temperature. And so for a nozzle, as it flows through, like if you think of a garden hose nozzle, the temperature of the water flowing through that garden hose nozzle is not going to increase a lot, okay? So yeah, it's not going to increase any measurable amount. So I'm going to go ahead and get rid of U1 and U2 because the difference in those are not going to factor in too much with this equation right here. So what we're just doing a scaling analysis just to see what the important terms are. And this is what I'm looking at. So what it tells me is that the pressure energy at the inlet has to be big enough to be the sum of the pressure energy at the outlet plus the kinetic energy at the outlet. So the pressure at the inlet has to be bigger than the pressure at the outlet. That's the upshot. All right, well, I hope that was helpful, and let me know if you have any questions.